You've watched the sun your whole life. It came up this morning and it'll come up again tomorrow. Every civilization that has ever looked at the sun treated it as one of the things that was never going anywhere. Permanent, eternal, the one constant. But it's going to die. And here's the part that's actually strange. We've known the sun rises and sets since forever, but we've only known it can die about 150 years ago. Before that, nobody could even prove it. Not because they didn't wonder, because nobody had a way to find out. Figuring it out took two of the most respected scientists on Earth getting the answer badly wrong. It took a fight between physics and geology that neither side could win. And it took almost 80 years to actually solve. We're not even fully done solving it. Let's start with the moment someone first tried to ask the question seriously. For basically all of human history, asking how does the sun die wasn't really a science question. It was a myth question. The sun was a god, or a chariot, or a fire that was just always going to be there. There was no tool, no math, no observation that could even approach it. That changed in the mid 1800s. Once physicists finally understood something basic. Energy doesn't come from nowhere. If the sun is putting out heat and light every single second, the energy has to be coming from somewhere. Which means whatever that source is, it can eventually run out. That one idea turned is the sun eternal from a myth question into a physics question for the first time in human history. And two of the biggest scientific names of the era decided to actually answer it. In the 1860s, a physicist named Lord Kelvin, the same person the temperature scale is named after, sat down to actually calculate it. At the time, the only real candidate for the sun's power source was gravity. Kelvin's idea, the sun is slowly collapsing in on itself, and that collapse releases heat, the same way rubbing your hand together warms them up. He ran the math on how long that process could keep the sun shining. His answer? Somewhere between 20 million to 100 million years. Not forever. A number. A real calculated expiration date. A physicist named Herman ran a similar calculation independently and landed in roughly the same range. Two of the sharpest minds in physics working the problem from the best tools available, agreeing with each other. Case closed. Except it wasn't. Because at the exact same time, a completely different group of scientists was staring at a number that made Kelvin's answer impossible. Here's the part that most people never hear about this story. The sun's expiration date wasn't settled by physicists. It was blown up by geologists. And for the next 50 years, nobody could explain why the two sides couldn't agree. While Kelvin was calculating tens of millions of years, geologists were digging through rock layers that told a completely different story. Erosion, sediment, and slow stacking of layer on layer, all of it pointed to a planet and a sun shining on it that had to be hundreds of millions of years old at minimum. Some argued for billions. Charles Darwin needed that kind of time too. Evolution by natural selection only works if there's been enough time for it to happen. And Kelvin's number wasn't close to enough. So now there were two respected, careful, mathematically solid answers. And they flatly contradicted each other. Kelvin didn't back down. If anything, he tightened his number over the following decades, insisting that geologists and Darwin were the ones that had it wrong. For nearly 50 years, the fight just sat there unresolved. Nobody could explain the gap because nobody yet knew about the one thing that would eventually solve it. They were missing an entire source of energy that physics hadn't discovered yet. Kelvin wasn't a bad scientist. He was working with the only physics that existed at the time. Gravity was the only known way to release that much energy. There was no other candidate on the table. His math was airtight. His starting assumption was just wrong, and there was no way for him to know yet. That's the uncomfortable part of this story. Being wrong here didn't come from carelessness. It came from not knowing what you don't know yet, which, if you think about it, is a pretty permanent problem in science. There's probably a version of this happening in some field right now, and none of us know it either. Speaking of things that are easy to miss, if you don't want to miss whatever we dig up next, subscribing handles that for you. Anyway, back to the sun. The missing piece finally showed up in the most unexpected place possible. It didn't come from a telescope. It didn't come from a geologist. It came from a physics paper that at first had nothing to do with the sun at all. In 1905, Albert Einstein published the equation E equals mc squared. In plain terms, mass and energy are the same thing, just in different forms. And a tiny amount of mass converts into an absolutely enormous amount of energy. Nobody connected it to the sun right away. It took until 1920 for an astronomer named Arthur Eddington to make the leap. Eddington proposed that the sun wasn't shining from slowly collapsing under gravity. It was shining because it was fusing hydrogen into helium in its core. And Einstein's equation explained exactly why the process released so much energy. At the time, most scientists thought Eddington was wrong. The core of the sun didn't seem hot enough for that kind of reaction to even start. Eddington's response became famous. He told the doubters to go find a hotter place. It took another 2 decades to actually prove him right. In 1939, physicist Hans Bethe worked out the precise nuclear steps, the exact chain reactions happening inside the sun's core, step by step. For the first time in human history, someone could point to a mechanism and say, this is what powers the sun, and this is what will eventually run out. 80 years after Kelvin's first calculation, the real answer finally existed. Here's the version Hans' work actually led to. A star shines because it's fusing hydrogen into helium in its core, and the fusion pushes outward against gravity, which is always trying to crush the star inward. For most of a star's life, those two forces stay balanced. A star dies when it runs low on the fuel needed to keep pushing back, and gravity starts to win. For a star like the sun, that doesn't mean a quiet collapse. It means swelling into a red giant, big enough to reach toward its nearest planets before gently breathing its outer layers into space and leaving behind a small, dense leftover core called a white dwarf. That's expected to happen in roughly 5 billion years. For much bigger stars, gravity is strong enough that they keep fusing heavier elements to hold themselves up. Helium, then carbon, and down the line until they hit iron. Iron is where fusion stops paying off. It costs energy instead of releasing it. So iron just piles up in the core until it can't support its own weight anymore and collapses in just about a second. Then rebounds outward in an explosion that could briefly outshine its own galaxy. Same starting question Kelvin and Herman asked in the 1960s. It just took 80 extra years and the right physics to actually answer it. You'd think that settles it. It doesn't. Even Hans' answer had a hole in it that took another 60 years to close. Hans' answer in 1939 wasn't actually the end of the story either. Once physicists knew exactly what reactions were happening in the sun's core, they realized those reactions should be producing a very specific number of tiny particles, called neutrinos, streaming out of the sun by the trillions every second. So starting in the late 1960s, a physicist named Ray Davis built a detector deep underground specifically to count them. He found about a third of what the math predicted. Not close, a third. For over 30 years, nobody could explain the gap. Some scientists wondered if the fusion theory itself was wrong after all. Decades after everyone thought the answer was closed. It wasn't solved until 2001, when a different detector showed the missing neutrinos weren't missing at all. They had been changing form on the way to Earth into types that the original detector simply couldn't see. The fusion theory was right the whole time. Nobody had known neutrinos could do that. So even after Kelvin, Eddington, and Hans, the sun still had one more way of proving people wrong. So the mystery that started with Kelvin in 1860s isn't actually closed. We solved the big piece, but we're still working on the rest. Every sunrise you've ever seen came from the same star Kelvin miscalculated, that Darwin needed more time from, that Eddington got laughed at for defending, It took 150 years, several of best scientists of the eras being wrong in public, and one equation that had nothing to do with astronomy at all, to prove something that feels obvious now. The sun isn't permanent. Next time you watch a sunset, you're not just looking at something that's always been there. You're looking at the answer to a question that took the entire scientific world a century and a half to actually earn. And we're still not finished asking it.